Hi, everyone. Before I start, I must confess I was so excited on Sunday to come to Porto that I had too many cold drinks and I lost my voice. So the sound quality is going to be shitty, probably, but I hope to compensate with the content. So I don't know how to press the button. Here we are. To introduce myself, so my name is Kirill Shirinkin. I'm the co-founder of MKDev and the cloud native consultant. In case you're wondering, this is my security dog. Hence, protects me from DHL deliveries. I'm very bad with this button. Here, okay. So MKDev is the DevOps and cloud native consultancy based in Germany. So what we do for our clients is the consultancy, workshops, audits, and assessments for public cloud, Kubernetes, and other topics. And of course, one of the things we specialize in is Kubernetes. As you know, like to do DevOps, you have to have Kubernetes, and every company needs it. But our job is actually to convince our customers sometimes that Kubernetes is not a good idea. And that will be partially the topic for today. So the agenda, to understand why we have Kubernetes, we need to go through a bit of a history lesson, how we ended up with the system like Kubernetes. Then we will talk about how it's going right now, how Kubernetes is being used, and some of the challenges with capacity management. And important here is the simplified part, because I will give you just a glimpse of all the challenges you might have with this topic in Kubernetes. And as a final part, I'll talk about where it's going. So what's the future of Kubernetes and how you should think about Kubernetes. So I'll start a bit with the historical part of how it started. And we need to start with hardware. So many years ago, the only thing we had was the bare metal machines. To run your application, you had to have a physical box with a fixed amount of CPU and RAM, and you deploy your apps there. And the issue with this is that you can never have like one physical box, so you need to have high availability, and also if the load increases on an application, you need to add another box. So the way you scale is you basically add another physical box, and you wait for delivery of this box, and then you wait for this to be cabled, and then you can use it. Naturally, it's a very long process. And you don't want to wait too long, so you end up having some pre-booked capacity. So you buy, let's say, 10 servers to handle all the potential load. The issue then is that you might handle the load, but you're probably wasting lots of resources. So maybe you utilize only 40%, and then you bought all of these machines that do nothing, and that's not so good, and then you cannot get rid of the capacity because you already bought the server, so you need to kind of sell it. Naturally, many companies just outsource this data center management to other providers who would do all the cabling and the bare metal stuff for them. But as a customer of these providers, we still have to think about, okay, when should we order a new one? How do we configure the servers? And what happens if we misconfigure this machine? We just basically need to reinstall the operating system, all these things. And all of this changes big time with the advance of virtualization, because what virtual machines gave us is that they took the physical concept, this physical server, and made it a software abstraction. So the server stopped being the physical thing, and it became a software. And it's especially important once we can outsource the physical layer to some other company like Amazon, because the only thing we deal with is with the software thing. And what should enable us to do is things like, okay, if we need more servers, we can just dynamically increase the amount of instances. And when we don't need them, we can reduce them. And we pay per second. So it used to be per minute, now it's per second in most of the cloud providers. And we get this elasticity and many, many features like, okay, we can easily resize the instance without waiting for the actual physical thing to be delivered. And of course, all this makes sense if you use the cloud, right? So if you have your own data center, you have still machines and the VMware or whatever other hypervisor. But with the cloud provider, you only deal with the software thing. And that's a big change, because now you're not limited by physical world anymore. You deal with software abstractions. And what cloud providers started doing is building more powerful abstractions on top of this, like database as a service. So, for example, Amazon RDS lets you provision the database cluster, and you think way less about underlying machines, virtual machines, and you think more in terms of the database clusters. And these first abstractions were really useful, but in the end, like when you deploy RDS or Cloud SQL, you still have this servers of certain size. So you create an instance with like 8 cores of RAM. So the next really big change appeared when cloud providers started building even more powerful abstractions on top of these virtual machines that they have. So you might know, for example, Amazon has the thing called SQS, Simple Queue Service. And with SQS, you never ever see servers again. So you have the queue, you pay for the amount of messages that goes through this queue, but you never see the servers behind it. And same, for example, for object storage. So you pay for number of objects for the storage, but you never see what are the virtual machines and especially the hardware behind the Amazon S3 bucket or the Google Cloud Store. And in my opinion, this is really the first serverless application. So when we talk about serverless today, we think about Lambda functions or like cloud functions. But really, this SQS, S3, and similar tools from cloud providers were the first really truly serverless abstractions because we just don't think about servers anymore. We think about, we pay for some things like messages, objects, and this stuff. The problem, though, is that cloud provider cannot abstract away your application. So you have like DynamoDB, SQS, S3, and all of the serverless things, but your application, like Amazon will not create abstraction for your application. So you still need to deploy this application on some server, and it still needs CPU, memory, and all of these things, not unlike the bare metal world, but of course with the capabilities of virtual machines. And the first step to make it a bit more abstract was the appearance of containers and container images as the packaging format, because once you package the application as the container image, then you don't need to do config management. You kind of have this completely, everything is included in this package. Naturally, container image has the operating system, but you don't deal with it the same way as with the virtual machine or the bare metal server. Once this packaging problem is kind of solved, and we can now run our container images practically anywhere, regardless if it's the container orchestrator or anywhere else, we had to come up with the tools that can run these containers at scale, so that we can basically scale out our container image to run with multiple replicas, and that's how Kubernetes appeared. So we got the Kubernetes to abstract away more and more things around running our own applications. The problem, though, is that all the previous layers are still there. So when you run a Kubernetes cluster, it runs somewhere, and then there is this mismatch between this new container abstractions, pods, deployments, and everything, and virtual machines under your cluster. And that's kind of the starting point for the next part of my talk, of the simplified version of capacity management with Kubernetes. So we have to start with the notion of pod. For simplicity, let's assume that one pod is one container, but really there could be multiple containers inside one pod. And your pod needs to run somewhere, right? So it does not run without a server. And let's take this picture. So it runs on a server which has 4 cores and 8 gigabytes of RAM, and you put the pod there. And you never specify how much CPU and RAM your pod needs because you think, well, Kubernetes is this great orchestrator that will just solve everything for me. In reality, what happens is that if you don't tell how much CPU and memory your pod needs, there's always a chance that pod goes out of the boundary of the server capacity and just kills your server. So it consumes all the CPU, the server is unresponsive, and you have to reboot it. So the default mode when you run application Kubernetes, your application can basically kill the node. It gets even better because, of course, Kubernetes is a self-healing system. So when your pod goes down, it gets rescheduled to the next node. But if your application is like behaving like shit, then it should kill the next node. And then it will be rescheduled to the third node. And it can go on and on until you lose a significant part of your Kubernetes cluster only because of this evil pod that has this unreasonable CPU or memory consumption pattern. Of course, this was solved. The way it's solved is that you set resources for your pod. And the way resources work is that you set requests and limits, and requests is the minimum. So there is like this light gray line is the minimum amount of resources that your pod needs, and there are limits, which is the maximum. So you say, okay, my pod always needs 1 CPU core, and sometimes it's actually the 2 CPU cores. So then 1 CPU is the minimum or request, and the 2 is the maximum. It's important to set this request because the way Kubernetes scheduler works, it looks at requests. So if you say, if you have a node which has, in this case, 4 cores, so there's like divided into 4 sections, and you have 3 pods, each requests 1 CPU core, Kubernetes will block these CPU cores for these 3 pods. And the problem here is, of course, so the orange block here represents utilization, and you see that we've requested 3 cores, but we utilized only 1.5 core. it means we waste 2.5 CPU cores on the node. And we can only place pods with the total number of 1 core extra on this particular server, even though in theory it can fit way more. The next concept we have to talk about is quality of a service. And this is something that you never configure in Kubernetes. It's something that Kubernetes does for you. If you go to your cluster and you say like kubectl get pods and the name of the pod minus o YAML, you will find quality of the service. And quality of the service is basically assigned based on your requests and limits. If your requests and limits are identical, so if you say my pod always needs 1 CPU core and it does not ever need more than 1 CPU core, it gets a guaranteed quality of the service, assuming that it's the same for memory. And if there is a gap between requests and limits, then it gets the burstable class. So it means like if you have some pod that does nothing for most of the time, then it spikes at the start or during some job, then you can have this burstable class. And if you don't specify any requests and limits, then your pod gets best effort quality of the service. And the issue is that best effort is best effort. So Kubernetes promises you that guaranteed pods are always prioritized. So they're the most important pod on the node. Second goes the burstable, and then the best effort. So the theory goes that if Kubernetes has to evacuate or remove some pod, it will remove first the best effort, and then the burstable, and then the guaranteed. The problem here is that best effort really means best effort, and if this best effort pod tries to just eat all the resources of this node, it will do it. So it's critical that all of your pods have resources and limits set. Otherwise, you have the time bomb all the time. So the good thing to do in this case is that for all of your pods in your cluster, you need to have resources set with limits and requests. It's preferable for applications that serve production traffic all the time to basically use guaranteed quality of your service, meaning that you set requests and limits to be the same value. And then for some less critical things where you kind of also want to save money and they don't really need the resources all the time, you set the burstable class. And with this kind of mix, it works relatively fine. The question then is, how much is the pod, right? So how do I understand how much CPU and memory you need to set? Because you spend the time creating the Kubernetes cluster, assigning the CPU and memory to your nodes, and now you need to do the same about the pods. And really, this topic deserves a whole other talk about how you can use metrics to kind of understand consumption patterns. If you're lucky and the application already runs on the legacy system, then you already have some kind of metrics to understand what you should use for requests and limits. If it's the brand new application and it goes on Kubernetes day one, you should start with the vertical pod autoscaler, which is the thing that gives you recommendations how much memory and CPU application uses based on the last 2 weeks, or more than 2 weeks if you plug in Prometheus. And once you understand this consumption pattern, you can also replace VPA with the horizontal pod autoscaler to enable this scaling out based on the load, which creates more pods when the load grows on the application. Maybe here you go. Sorry, it's like an 8K slide, it takes time to load. Okay, we talked about pods. Now let's talk about the nodes, because your pods are running on the nodes. Let's take this picture. We have 2 nodes, 2 CPU cores each. We have on each node 2 pods. So it means, regardless of utilization, it's a really important point that utilization is never looked at. These nodes are booked. You cannot run any pods on them. So if you have another pod and tell like, okay, Kubernetes, please run it, it just needs like 200 millicores, Kubernetes will say no because all pods are booked, and you'll get the message like no nodes available for scheduling. Okay. So coming back to this point, even if your cluster nodes are underutilized, as long as everything is requested and you need to run the pod with 2 cores, you cannot place it here. So in this picture, again, we use only 1.5 core on this Kubernetes node, but 3 of them are reserved, so you're wasting the space, basically. Okay. Or, to take it even more visually, is that this light gray area is how much is utilized, and the dark gray is how much is requested. So you see this pod, it can fit really well on both of the nodes, but only the white space is not requested by any other pod, so there is no space for this pod on these 2 nodes. This latency is killing me with the slides. I was told like there is no latency with the clicker, but it's not. So yeah, come back to this picture. There is no way to run because all cores are requested. Am I doing something? So you need a cluster autoscaler. So cluster autoscaler is this component that you can run, and it's not part of Kubernetes, right? So you have to actually install and configure it yourself, and it depends on the cloud provider how it works. So it's like a separate open source thing that will create more nodes as the demand grows. And the way cluster autoscaler is working is that it sees that you have, for example, 10 CPU cores, but all 10 are requested, and now you want to run another pod with 2 more cores, so it creates a new node. Again, never looks at utilization. Utilization is never taken into consideration, but Kubernetes, it looks at requests. And then it creates a new node, and then your pod is successfully scheduled. And depending on the cloud provider, it can take like 1-2 minutes for this new node to appear and to start hosting your pods. So this is good. Now, once you have this another component figured out, you can scale out. The problem is, let's say these nodes are 8 CPU cores and 16 gigs of RAM. And you try to run a pod that needs 20 CPU cores because it's like some, I don't know, parser from security team to go through all of the Git repositories, and it needs really much CPU. There is no way for the cluster autoscaler to autoscale your nodes to fit this pod because you said, I have these 8 CPU core nodes. You can add as many of them as you'd like, but if your pod is 20 CPU cores, there is no way to put it. And you have 2 options to solve it. So you can create a heterogeneous cluster, which means you have nodes of different sizes. So you can have like really big nodes, you have nodes with the GPU attached, and you configure cluster autoscaler to scale them independently, and you make sure that utilization is okay. What is actually always preferred is that you just create more clusters for different purposes. So for your core applications that serve the production traffic, you create like a core cluster. For your data science team, you create machine learning cluster, maybe with the GPUs and maybe even the bare metal. And then you can have another cluster for the batch jobs or for the CI jobs, which has, for example, like spot instances and smaller SLAs and less expectations on the availability. And there is no right answer, like how many clusters, how you should them configure, because it really depends on your use case, right? So if you have only one web application, of course, go with like one cluster with the homogeneous nodes. If you have many, many services, many apps, then you have to really be strategic about how many clusters you create and how to configure them. So now a bit of a quiz time. What happens if your pod requests 2 gigs of RAM? It limits it to 10 gigs of RAM, but the maximum memory of your node is 6 gigs of RAM. Or the mirror question, what happens if you do the same with the CPU? So the answer is, well, limits are never considered by the scheduler. So it will never check that you don't even have the node with this kind of amount of memory. So it will put the pod on the existing node because requests are fitting, so it can put it there. And then this pod tries to use all of the CPU or all of the memory, and then you have a disruption. So other pods get killed, the node maybe is rendered unresponsive, this pod gets rescheduled to another node, then the another node dies, and that's it. So how do we fix it? And the answer is you don't. At this point, you lost. Like, you lost the Kubernetes capacity game. You should give up and use ECS. You should use virtual machines or anything else. OK, of course, there is a way out. The first step to get out of the situation is that you get the quotas. So the quota is this amount of resources your Kubernetes namespace can use. So you can create namespaces for different teams, for different applications, and then you attach the quota to this namespace saying like, OK, this team can only use like 10 CPU cores and 20 gigs of RAM. And then this very important project can have a bigger quota. Once you have this configured and automated, and remember, like you cannot configure it by hand, so you need to have like a repository or any other kind of platform automation to provision these namespaces, you can configure limit range. A limit range is a curious object because this one actually restricts, it's like a policy for how many resources pods can request. And it works for many types of resources, like for the storage and everything, but important for this discussion, the CPU and memory. In limit range, you can set, so the light gray is the request, the dark violet gray is the limits, and the blue one is the limit range value for the maximum amount of resources you can request per pod. So if you know that you have only 8 gigs of RAM nodes in your cluster, you just set a limit range to cap the maximum memory per pod to be 8 gigs, or like 7 gigs, because it's a bit stupid if you have nodes with 8 gigs and then you limit range to 8 gigs. And you can also do the same for the minimum, so you can say every pod needs a minimum of like 1 core or 150 millicores. And to actually solve the issue that we just saw before, you can also set the request limit ratio. And this option allows you to say like, okay, the ratio is 1.5, meaning that if you set CPU request to 1 core, you can set limit maximum to 1.5 cores. So it kind of keeps such constraints, so it prevents you from having this stupid pods that like request 100 millicores and limit to like 100 cores, which, as I said, they can kill the cluster. And at this point, you win the Kubernetes Capacity Management game, the simplified version of it. So as I said, it's intentionally simplified talk because there are many, many more things about how you place pods, anti-affinity rules, topology sprays, how you pin the pods based on if the node has the GPU and all these other things. But let's say, if you go through the cluster autoscaler, request limits, resource quotas, and limit ranges, then you'll probably be fine. So your cluster will run OK for most of the time. Of course, it's a big job for you to figure out correct utilization because you can configure requests and limits, and the cluster will be stable and run smoothly, but you'll be utilizing like 10%. So you need some kind of monitoring to figure out if you're actually utilizing what you requested in the cluster. But as I said, like, you'll be okay with all of these things. The question is, was it worth the effort to configure all of this capacity management for a cluster? Because if you look at this, in such cluster, you have the same concept applied twice. So you have this virtual machine world with like EC2 instances or whatever other kind of virtual servers you have, where you need to carefully understand how many resources to configure per node. You need to configure auto-scaling for these instances, because in the end, like in Amazon, for example, this left part is done with the auto-scaling groups. It's exactly the same auto-scaling groups that you have outside of Kubernetes. But then on top of this layer, with the cluster autoscaler, with the instances, with the virtual machines, and luckily you don't have to think about the lower level of the hardware because that's already handled by the cloud provider. So on top of this, you have this thing with the pods, where you also need to understand the utilization. You need to figure out how much CPU and memory it needs. You need to configure the auto-scaling with the concrete thresholds when to trigger the scaling events. So you have this thing like kind of twice, and you need to manage both of them on the virtual machine and pod level, and also to build all the links so that it kind of works smoothly. And if you think about it, that's not entirely different from what would you do 10 years ago with just EC2 instances and auto-scaling groups. You could create the auto-scaling group for your application. You could actually define auto-scaling based on utilization because you don't have these two layers, one on top of another. So you can just say, when utilization is 80%, create more EC2 instances. With Kubernetes, you can do it because it looks at requests, so utilization is kind of hidden from you. And you could use AMIs or any other virtual machine images. You could build it with the Packer in your CI/CD pipeline, and the result is the same. You have a package with your application inside, immutable package, and you roll out with the auto-scaling group. So you need to think about, like, does it actually make sense to go through the trouble of Kubernetes? It doesn't mean Kubernetes is bad, and now let's talk about where it's going. So what's the future of this? Should we kind of stop using Kubernetes, or is there something more in it? But the first thing that is happening right now is that Kubernetes is going serverless. So if you go to Amazon, for example, Amazon has this idea of serverless Kubernetes that there are no nodes at all, and the way they implement it with this technology called AWS Fargate, which allocates for every pod a micro virtual machine. So each pod becomes the node in the API, but like you don't treat it as the node. You just have pods, and you say this pod needs 2 CPU cores, and that's all you think about. You never think about another thing underneath, which also has CPU and memory. Another approach is taken by the Google Cloud. They have the G-key autopilot, and autopilot kind of tries to, when you request the pods, it finds the correct combination of the nodes where to put the pods on. The result is the same. The nodes kind of disappear, so they disappear in a different way. In Fargate, you don't have the nodes. In Google Cloud, you don't think about them, but they're still there. There's also an open source project called Carpenter. This is from Amazon, and it's like open source G-key autopilot for AWS, which works a bit different than cluster autoscaler because you say, okay, my pod needs 6 CPU cores. Carpenter will also find an instance that can fit this pod. Similar to autopilot, as I said. Of course, it's not perfect. Like Fargate sometimes works like total shit. Like you need 1 minute to create a single pod, which is quite slow, right? Especially if you try to use Kubernetes for the CI/CD jobs, this is horrible. You don't want to wait 1 minute for the CI pod to appear. But one thing is for certain is that any cloud provider will improve over time, and they'll probably improve over time way faster than your organization because they focus on making Fargate work, or they focus on making GKE autopilot work. So even there are some disadvantages in these serverless approaches right now, in 3-4 years, I think it should be kind of, you would need to have really good reasons to run Kubernetes nodes on your own and not just use serverless offering from one of the cloud providers. Then the question is, once Kubernetes is serverless, what is Kubernetes? Because definitely it's not an orchestrator, it's not a scheduler anymore, because you don't have any nodes, and you just say, I want to run pods, and then they're just there. There is nothing underneath. Well, first of all, of course, Kubernetes is a set of abstractions, and that's one of the original reasons we use it, is because it's this very powerful software abstraction that we can use to define our applications, so you have deployment. And this deployment abstraction works on any Kubernetes cluster, regardless if it's Amazon or Google Cloud. Same goes for service, ingress, and all the other persistent volume, secret, other stuff. So you don't need to think about configuration files. You don't need to think about like Puppet or Chef to configure something on the instance, some bar scripts. You have this really application-focused primitives that Kubernetes gives you. But the second thing, what enables these primitives, is that Kubernetes is an API. Quite often exposed to you as the nice YAML files, where you just say, okay, I need the deployment with this particular setting, this number of replicas. But what's probably even more important, becomes more important over the last years, and will be more important in the future, is that Kubernetes is the API that you can extend. So these objects, so these ones and the built-in ones, they're not fixed in stone. And Kubernetes lets you define any other abstraction that you like with the thing called custom resource definitions and the custom controllers. You can basically create a new type of things for a cluster. For example, this is the snippet from the Jenkins controller. You can just say to Kubernetes, I want to run Jenkins. You don't say, I want to run 5 containers with the CPU memory. No, you just say, I need Jenkins. And once Kubernetes is serverless, it will run you Jenkins without any considerations for the nodes, because there are no more nodes. Another example is this Postgres operator from Zalando. And look how many application-specific things are in there. So, of course, there is a number of instances in the storage size, but there is like users and databases. So, really application-specific abstractions that Zalando built for Postgres. That is completely, like, it doesn't know about virtual machines. The user, so it doesn't have to think about like all binding together all the standard Kubernetes objects. And even more curious new layer of abstractions that cloud providers are building, and this is something that Google and Amazon has, I'm not sure about Azure, is something called, Google calls it config connector, Amazon calls it AWS Kubernetes controllers. It lets you create cloud resources with YAMLs. So in this case, you create a S3 bucket with your Kubernetes API, but there is nothing in the cluster, right? So there is just a software abstraction to create a bucket, but there are no pods, there are no services. So to conclude, there is this excellent book called Beginning of Infinity from one of the quantum computing pioneers called David Deutsch. And he has a chapter called The Jump to Universality. And he defines it as the tendency of gradually improving systems to undergo a sudden large increase in functionality, becoming universal in some domain. One example of this is the alphabet. So alphabet is universal enough to create any kind of language. So you can build unlimited number of words and sentences and books and talks because it's a universal system. So at some point, humanity jumped from like 3-4 words to the alphabet, which was the universal system that allow us to build infinitely many languages and capabilities to communicate. And I think it's useful to think about Kubernetes, especially in the future, maybe not right now, as this jump to universality of infrastructure abstractions. Because this third stage of serverless abstractions was defined by the cloud providers. So the Amazon decided for users there is this SQS abstraction and how it works. But now with Kubernetes, you can define your own abstractions. So you're free to define Postgres, Jenkins, some still application specific. So you can say like my company name application, custom resource definition, and deploy your particular app. And yeah, take a look, once the Kubernetes becomes serverless, I think that should be the main value of Kubernetes. That's all I have. Thanks for listening, and let's have a chat about this topic afterwards. Sorry.
So someone has any question for our speaker?
Ras. Thank you, Kirill, for the talk. I have a question, maybe it's a bit specific. So it's more or less clear how to deal with memory limits and requests. But what about CPU limits? So I heard approach that it makes no sense to define CPU limits for some workloads. So based on your experience, what could be the way? Should we define the CPU limits for this exact workload or not?
Yeah, I was in the blog post about the CPU limits make no sense. And partially it's true because with the CPU processor, the CPU itself is kind of more efficient with scheduling. But you will always be at risk. For example, 1 year ago, the Thanos, this part of Prometheus, to make Prometheus highly available, had a bug that basically just causes CPU to be always to 100% and just makes the node unresponsive. So once it's unlimited and you have this open source component, it's still a problem without the limits. And you need to keep in mind that in your cluster, it's not only your applications. For example, the cluster autoscaler is also an application running in a cluster, and you need to trust that developers of cluster autoscaler will not release a bug that, again, makes CPU consumption unreasonable. So you still need to kind of limit. Probably for some cases, it makes no sense to set the CPU limit, and it also depends on how the operating system works, because there could be like Red Hat Linux works differently from some immutable container operating system in terms of the scheduling, in terms like which system level tool it uses to schedule the processes. So, yeah.
Okay, thank you.
Thank you very much. A big round of applause to our speaker.
Okay. Okay.